Okay, looking just at, again, the fact that our y equals 1 over x function has a graph that looks like this with its asymptotes to the y and x axis and its symmetry with respect to the origin, which gives you a negative asymptote on the y axis as opposed to the positive one here, and a horizontal asymptote below the x axis as opposed to the horizontal asymptote above the x axis in the first quadrant. Our graph of y equals 1 over x minus 3 just translates this graph 3 units to the right, giving us an asymptote excuse me, below the x-axis in the negative direction, an asymptote above the x-axis as we go away from the x equals 3 in the positive direction, and at the line x equals 3, an asymptote going to plus infinity, an asymptote with positive values to the x equals 3 line, and on the left, an asymptote with negative values. We note again that for y equals 1 over x, as x goes to 0, 1 over x exceeds any bound you might choose. If you let x be small enough, you can make 1 over x as big as you like. So that this graph has no limit to its height, but it never touches the y-axis. Okay, now we look at the function h of x equals x plus 3 over the quantity x minus 2 times the quantity x plus 4. Again, we have linear factors, but we have a polynomial in the numerator and a polynomial in the denominator. In order to graph this function, we start by finding its intercepts. Well, the x-intercept occurs when y equals 0, which means that x plus 3 over x minus 2 times x plus 4 has to equal 0. So the function has value 0, y equals h of x is 0, if this is the case. If we multiply both sides of this equation by x minus 2 times x plus 4, we get x plus 3 equals 0. And that is equivalent to the original equation, provided x is not equal to 2, which would make x minus 2 0, or to negative 4, which would make x plus 4 0, because we can't multiply both sides of the equation by 0 and get an equivalent equation. If we multiply both sides of the equation by 0, it just wipes everything out. Okay. So, for all x values except x equals 2 and x equals negative 4, this is equivalent to this, and this tells you that x equals negative 3. And since negative 3 is not equal to 2 or to negative 4, then this is a 0 of the function. So we solve the equation, set the expression equal to 0, multiply through by the denominator, get our solution, make sure that that solution is not also a 0 of the denominator, then it's a 0 of the function. And maybe I need to have a couple extra words in there to make clear what I mean by a 0, since I just used it in application to the denominator and to the function. Okay, so now it's clear that x equals negative 3 is a 0 of h of x, which is our function. The y-intercept is easily found. You let x equal 0. If you put in x equals 0, I leave it to you to evaluate, you get 3/8, negative 3/8. So the y-intercept is negative 3/8. Now, we next move to discussion of asymptotes. Okay, vertical asymptotes especially are important when we're graphing these functions. Vertical asymptotes occur when the denominator approaches 0 and the numerator doesn't. Okay, so question, for what values of the denominator, or near what values of the denominator will x approach 0? And I didn't say that right. For what values of x will the value of the denominator approach 0? Okay, so denominator is x minus 2 times x plus 4. We know when x equals 2, the denominator is going to be 0. When x equals negative 4, it's going to be 0. As x approaches 2, x minus 2 approaches 0, which means that the denominator approaches 0. Now, when x approaches 2, the numerator is going to be close to 5. 2 plus 3 is 5. So we're dividing 5 by a denominator that's approaching 0. We're dividing a number that stays very close to 5 by a denominator that approaches 0. So if the denominator is close to 0 when x is close to 2 or when x is close to -4. Okay, close to 2 we're dividing by a number that approaches 0, and the same thing is true when x is close to -4. The denominator is going to approach 0. The numerator is going to stay, well, -4 plus 3 is -1, and the numerator is not going to change much as x gets closer to -4. Okay, so I say numerator isn't close to 0 when x is 2 or x equals -4, and it follows then that we get vertical asymptotes when x equals 2 and when x equals -4. So now we're going to draw the information that we have about the function on a slightly expanded graph, just like this graph, but my x-axis is a little straighter down here. But more importantly, I've got my asymptote at -4, my vertical asymptote at x equals -4, and my vertical asymptote at x equals 2. Now we know x can change sign at -3, or it might not change sign at -3. X can also, h of x, our function, can change sign at x equals 3. It might or might not. We'll have to test and see. But there are also other points where it could change sign. Now, before we had a polynomial function which had a continuous uninterrupted graph. The graph of a rational function where you have a denominator that could approach 0 is not continuous and uninterrupted. We can see that either of these graphs, the y equal 1 over x minus 3 graph, is interrupted here at the asymptote. There's no point on the graph corresponding to x equals 3 because division by 0 is undefined. So the graph actually has a break at this point. So it can go from negative to positive at an asymptote, and as this one does. Now it might not go from negative to positive. It might stay negative on both sides or positive on both sides. For example, if you had y equals 1 over x squared, you can verify that the graph is going to look something like this. You still have an asymptote, a point where the function is not defined, but it doesn't change sign. And we saw with polynomials, you can have zeros where the polynomial doesn't change sign, maybe comes up here and just touches this point and goes around, right? So it acts like a parabola at that point. Similarly, at an asymptote, we can either change sign or we can not change sign. At a 0, we can change sign by going straight through like a linear function, or there are other ways. Or we can have something that's much like a parabola, a quadratic function, and doesn't go through the 0. Okay, well, the bottom line then is that we have intervals on which the function has to have the same sign. Okay, to the left of x equals -4, there are no asymptotes and no zeros, so there's no way for the value of our function h of x to change sign to the left of x equals -4. However, x equals -4 is a vertical asymptote, so the function could or could not, depending, change sign as we go from the left of x equals -4 to the right. So maybe it changes sign here, maybe it doesn't, but it certainly doesn't change sign to the left of x equals -4. Now, the next opportunity the function has to change sign is at x equals -3. So between -4 and -3, the function is always going to have the same sign. Then, between x equals 3 and x equals -3, between x equals -3 and x equals 2, again, no opportunity to change sign, so the function will have the same value between here and here. And then to the right of x equals 2. Now at x equals 2, the function again could change sign. You have a vertical asymptote. We could go from this to this, or from this to this at that asymptote. But after x equals 2, beyond that, there's not going to be any change in the sign. Now we'll use this behavior at asymptotes, and the checking we'll check the signs on each of these 4 intervals, and then we'll be able to construct some semblance of the graph.